Morning. So last week we have proved the existence of the solution when the source term f is C1, and then we have introduced the concept of Helder continuous functions. So let me recall once again the definition of the Helder continuity. So we have f is said to be Helder continuous. Quickly let me go through it. Continuous at x0 if there is a constant which satisfies this inequality, right? So this inequality is satisfied at x0. After that, we have introduced the uniform continuity. You need this estimate to satisfy for all x and y and uniformly. So there is a C which exists for that one. And then we have introduced local Helder continuity. When the local Helder continuity means it is uniformly Helder continuous for every compact subset of R. And then we have, using that one, we have introduced a space. We have introduced a space C0 of omega. Okay, and then for that we have introduced the no. So this is the usual no which you will see. Okay, and then you see this is the additional term added for the constant. So this norm is supranorm. So in addition to that, you have an extra property. You have to, whenever you are defining a norm, and if you want to recover that property should be embedded in your norm definition. If you don't include that extra property which you are defined in the norm, this will not recover that property when you do a limiting analysis. And with this it's a Banach space. You also define the higher order Helder continuous function Ck of alpha. So you're looking for all k times continuously differentiable functions, and its kth derivative is Helder continuous. Of course, below that lower derivative is already derivative exists, so you don't have to worry about the Helder continuity. The highest derivative will be continuous, but it may not be Helder continuous. So looking for only those f for which the highest derivative, kth derivative, all possible kth derivative, that's what it is written by beta here. Okay, so it is written by beta. Okay, for all beta with equal to k, so the all kth derivative, all possible kth derivative for which you can define a norm there. So now what we are going to do is that, so you have two things to be done. So you have your Newtonian potential. Let me again and again call Newtonian potential because that's the main thing. Okay, potential Bx is equal to integral over phi of x minus y f of y dy. Okay, so you want to understand the derivative. So we want to understand dv by dxi and d square v by dxi squared. Dxi xt. This is bit easy, relatively easy, because relatively easy. This is more difficult. The reason is local integrability. Relatively easy since d phi by dxi locally integrable. Now you see there is no differentiability, so you cannot immediately take the derivative to f, which we have done last time. When f is differentiable, you could take the differentiation to f, not to phi, because it's in the convolution form. So it's enough to take the differentiation to one of them. And f is differentiable, you can. But here now you have to deal with f phi only. But you have little extra f. I will tell you why it will get motivated later. But that is for this part. It's enough to this part we will use that Helder continuity part. Here it's not that important. But still it is not easy because you have to work with the phi. So you need what is called, here is the place I need regularization. I will explain to you how we do the regularization. So you want to out. This is what in maths you will do it. Whenever there is a singularity, you look for a neighborhood and try to work outside the neighborhood and then pass to the limit. That's the technique we will use it. So what we want to claim. So our claim is, so that let me take the theorem here. So let me write down the theorem. Omega bounded open as usual, open, and f from, so going to a special case we are considering, f from omega to r is, so I am assuming not the differentiability, but I am assuming boundedness, bounded and integrable, okay, not even continuity, okay. Then then the Newtonian potential V is in C1 of Rn. In fact, this is defined for all x, right? And for x in omega, and we are interested in omega because Vx is defined. If you look at the definition, Vx is defined for all x basically. Okay, so there's no issue, but our issue is for all x in omega. We have dv by dxi. This is what to be proved. Xi, this is what we expect because of the local integrability. Okay. Xi x minus y f of y dy. I will try to give a proof of this one. This is omega. Okay, so this is our of x, and this is what you want to prove. Okay. So let me try to give a proof. First we have to understand that one. Proof. Since so dv by dxi is locally integrable, and here we use boundedness. F is bounded and integrable, otherwise product of two integrable function need not be integrable when it is bounded. That implies dv by dxi x minus y f of y for each x is integrable. That's the first observation, and that means RHS is well defined as a finite quantity. RHS is well defined. Therefore, define that value. We don't know that is dy dx, so we will define wi of x is equal to integral over omega dv by dxi x minus y f of y dy, and immediately modulus of wi of x is finite. Integrable means the modulus is finite, so it's a well defined quantity. So you have to show, so the claim, what you want to prove is claim wi of x is equal to dv by dx. You want to show this. So here is where now we may require some regularization procedure. Okay, so I'll do a so let me do a regularization first, because there is a singularity at x equal to y. So I want to remove that singularity. Regularization to do the analysis. So I choose a function. So let me geometrically show you. So I want to choose a function. This is 1. So this is 1 here, 2 here. So I choose a function which is 0 here, smoothly varying, okay, and 1 here. So I am choose h in C1 of R. Okay, h at t is equal to 0 for t less than or equal to 1, and h at t is equal to 1 for t greater than or equal to 2, and h is C1, and you have a bound there. So you assume your h prime of t, so it's bounded thing because it's a C1. Here 0, here the derivative will be 0, so naturally it will be bounded. So I assume this is for some a. So this can be done. So with this I can define my h epsilon. So I can define for h epsilon not only in R, I can define h epsilon in Rn. You see, I will define h of mod x by epsilon. So when n equal to 1, how do you get this one? N equal to 1, it looks like this. So you will have epsilon here. This is epsilon positive. N equal to 1, 2 epsilon. So it will be like this. It will be, and here the derivative will not be. So if you look at it, here the derivative, if you compute h epsilon prime, if you compute, it will bring some excise here. So there will be something here, but divided by epsilon. So you compute this one and h prime. So you can compute mod x by that. So you can do something will be there. You see. So, but then so the derivative as epsilon goes to 0, the derivative may, even though this is bounded, that there will be a factor epsilon here. Okay, in higher dimension it will be something different. For each derivative you can compute that one. So for higher dimensions, how does it look like? So higher dimensions, it will look like n greater than or equal to 2. So it will be h epsilon will be something like that. You may have a ball of radius 1 and you may have a ball of radius. Okay, so this is 1, this is 2. Okay, and so h epsilon, yeah, this is ball of radius epsilon, this is ball of radius 2 epsilon. So h epsilon equal to 0 here, h epsilon equal to 1. These are all tricks you regularly use in PDE. And 0, you get 0 less than or equal to h epsilon less than or equal to 1. So you can do that also. Here 0 less than or equal to h less than or equal to 1, and smooth. So you have a smooth compactly supported function. The important thing is that in a neighborhood of epsilon it will be 0. So, and you know that phi has singularity when x equal to y. So if you are considering phi of x minus y, it has a singularity. So you use h around that point and make that singularity, remove it. So with this, sorry. Okay. Okay. All right. With this, let me introduce. So you introduce an approximation. Introduce Wi epsilon of x is equal to, or I can introduce something else. So yeah, first we will introduce both. Okay, W, not W epsilon. So the Vi is the problem. Okay, so introduce V epsilon. V epsilon of x is equal to integral over omega phi of x minus y h epsilon of x. You see, this is where I am using it. H epsilon of x minus y. Okay, h epsilon, I put epsilon up. So let me follow that. H epsilon x minus y f of y dy equal to this. Now look at this one. This is equal to 0 for mod x minus y is less than or equal to epsilon, and this is where the place it has singularity. So there is no singularity now for this function. So in fact, this is nothing but integral of mod x minus y greater than or equal to epsilon, this set intersection omega. So, and then this is the term here. So you see, so there is no singularity, so you can take immediately the derivative inside, and inside it's everything is nice, so you can take the derivative inside. Take the derivative inside because there is no singularity now. Smooth derivative inside, and this is a convolution form, so it's enough to take the derivative here. Whenever you have a convolution form, and if you are taking the derivative, you have to take the derivative with respect to that, and to get it, which will imply your dv epsilon by dxi. You see, by regularizing I can do that. I removed this one, so I want to prove, of course, integral over omega d by dxi of phi of x minus y and h epsilon of x minus y. In case epsilon I write it below, don't worry about it, f of y dy. Now I want to show that this precisely converges to wy, which is nothing but my dv by dxi. So that's the basic aim I want to show. Epsilon. So I want to compute now wi of x, which is defined minus dv by dx. Okay, that's x is equal to, now look at here again. As I said, there is near the neighborhood, there is no problem, it is x minus y less than or equal to epsilon, greater than or equal to epsilon, because it's the same thing. I didn't write it here, so it's basically integral mod x minus y greater than or equal to epsilon. Now when I do subtract this thing, h epsilon is equal to 1 for mod x minus y greater than or equal to 2 epsilon. So you have to understand that h epsilon is equal to 1, h epsilon of x minus y, if I compute, this will be greater than or equal, this is equal to 1 if mod x minus y greater than or equal to epsilon. And that is exactly the integral in your wi of x. So you look at your definition of wi of x is dphi by dxi f of y. Is that one. So if you look at it, this case, this equation, so if you work it out, so h epsilon will be 1 with, which is the same as wi. So if I do the subtraction for mod x minus y greater than or equal to epsilon, it will get cancelled because h epsilon equal to 1, which is the same as wi. So if you do that one, so I will get only this integral over epsilon. The singularity is removed, away from this also removed. Less than or equal to 2 epsilon. This is less than or equal to epsilon. Okay, so you will get this thing only inside that one. So you can, I can write down, so this is exactly equal to d by dxi. Here it is 1, only in this interval hs as other than 0 or 1 value. So you will have 1 minus h epsilon of x minus y. So to understand, this is a little trick you do it, regularization, phi of x minus y This is integration is with respect to differentiation is with respect to x and dy. Now I do an integration by parts here. Not integration by parts. I will expand that one. If I expand that one, of course this is, I will write only this second part. This part anyway it is 0. So whether you write it or not, it doesn't matter. If you want, you can write it. But this is not important to write this part because there is no singularity thing. Now look at here. So I integrate here. So if I differentiate this one, you will have minus dh epsilon by dxi at x minus y into phi of x minus y. And then you will have 1 plus 1 minus h epsilon of x minus y into d phi by dxi. There is no singularity. Okay. This is equal to your f of y. Now I will not do, you can do a bit of an analysis. So you use the bounds now. See, this is a bounded quantity. The derivative bound with respect to an epsilon. So there will be an epsilon coming in the denominator. Okay. So you can estimate there is an epsilon coming. On this case, this is less than or equal to 1. So if I compute this one, modulus of, therefore, modulus of wi of x minus d, there is an epsilon here, dv epsilon by dxi. If I compute this one, this will be less than or equal to integral over mod x minus y less than or equal to 2 epsilon. If you want, you put it this also here, and this can be bounded with an epsilon and a because the derivative is bounded thing, but when you differentiate it will bring up an epsilon, so that will be less than or equal to before that there is also a bound you can do. This one there will be an a over epsilon is, and this will be less than or equal to 1, so it is phi of x minus y. Modulus doesn't matter because it's anyway non-negative number, plus this is less than or equal to 1, so you will have d phi by dxi, and then dy, this is also x minus y, and then f you can take it as a bound inside, so I can bring it here, that one, norm of f at 0, that supremum norm you can bring it here. Now look here, you know this is the fundamental solution and it has its own estimate, and this will have an estimate here. So this will have an extra epsilon. In a small epsilon, when you estimate, so you have to estimate only in this ball. When you estimate in this ball, it will bring up an additional not only epsilon, for example n greater than 2, it will bring epsilon square. So 1 epsilon will get cancelled. On the other hand, this will bring only 1 epsilon. But then there is nothing epsilon to cancel. So this will bring thing. So this I will leave it as a small exercise for you, which we have done it essentially in the PDE course. You can prove this is less than or equal to a constant. This will be a constant. So this will bring an epsilon extra. This will also bring, this will bring in n greater than or equal to 3, it will bring some epsilon square. So that will bring epsilon, and this will bring an epsilon if n greater than or equal to 2. But n equal to 2, it will be something like a logarithm. So you will have epsilon. So there will be little less than epsilon. So because 1 plus log, but this is a 0 quantity which is log a epsilon. You can exactly calculate this if n equal to 2. Okay. So you see. So as epsilon goes to 0, so therefore you have the correct estimate. These are the estimates. So as epsilon goes to 0, you already know that v epsilon converges to v. That we know it. And now you are also proved that your dv epsilon by dxi will converge to your wi. this will, from here you can actually get it. Maybe I can do a little thing from here. This will imply your V is in C1 of Rn basically in omega, whatever it is, and that you already know, and dV by dxi is nothing but Wi. To prove this, what you do is that take some test functions and work out. You take some, what do you say, z in d omega. This is how you prove such things. You take z in one thing and then you compute your, so this is dv epsilon, so you compute your dv epsilon by dxi z. This is by integration. Z is compactly supported. This will be v epsilon dz by dxi, because this is a d omega function. Oh, this I have not introduced, is a C2 function. Yeah, so you don't need this. Let me not introduce this one. So you have a twice continuous. Once this will do. Even one will do. Once compactly supported function in omega. So you have this one. So there is no boundary term. But v epsilon converges to v. So this converges to minus integral over v dz by dxi, and this you have shown that this converges to integral over wi z. So you have this equality which will imply dv by dxi equal to w. Okay, so you have proved the theorem here. Okay, so what we have proved is that basically we have proved via regularization wi is equal to dv by dxi. That's nothing but dv by dxi. You can take the differentiation. So it's only the kind of regularization that will do. But then the problem with the second derivative is not locally. This we could do because it's all local integrable function. So there is no issue. Okay, so the just regularization you could manage it. So let me give a heuristic argument before concluding this lecture. Some y-Helder continuity now. Okay, y. So I will just give y-Helder continuity and then I will stop here. Helder continuity. A heuristic argument. Heuristic argument. Okay, so all right, so what do we want to do it? So we want to understand this term, right? That's just like previously we want to get d square v by dxi dxt. Equivalently, we need to understand second derivative inside. That's what we need to understand. Integral d square phi by dxi dxj f of y x minus y f of y dy. So this is where we want to understand. But this is not, so if you use this one, not locally integrable. Locally integrable. That implies the integral is not meaningful. The integral is not well defined. You see, that's where we have an issue. Because you know that d square phi by dxi dxj xi dxj behaves like, singularity is behaves like 1 by mod x minus y power n. And you know already that this is where you have to make a remark. Here we know one by in Rn 1 by mod, let me take the singularity at the origin. 1 by mod x power k is integrable in Rn, or locally integrable, only singularity is integrable in Rn. Okay, so let me take local integrability if and only if, this is an if and only if condition when k is strictly less than n. So k equal to n is not locally integrable. Not locally integrable. But if you anything less, little less, suppose 1 by mod x power, say n minus some epsilon, some alpha, so is locally integrable. For integrable for 0 less than alpha less than 1. So if there is a little less singularity, anything small singularity, like 1 by x minus 5 power n minus, say, alpha 0 less than alpha 1, it is locally integrable. And this alpha is what? This is the alpha we are looking through here. This is the alpha, because we cannot remove the singularity from phi. So this is the alpha we are looking through f. Looking through f. So we basically, so you have to think, so we consider the term basically, so to play with it, so we consider the term of the form d square phi by dxi dxj at x minus y into f of x minus f of y. So if you try to estimate this now, this will give you some constant by mod x minus y power n, and this will give you some mod x minus y power alpha, which is same as constant by 1 by, of course you have to play with it, mod x minus y power alpha n minus 1. So the extra singularity just at the boundary given produced by your fundamental solution is what is to be compensated from the source term, to have eventually the existence of the solution for your potential theory. So this is locally integrable. So you see, so this one together is locally integrable. So we will do more on this one, and we will eventually prove your final theorem in the next class. Okay, thank you.